about the multi-core programming, which is mostly about, let's say, the multi-core related software development parts, where I will discuss about the fork join parallelism. Also, I will give you the very brief idea of map reduce concept. Then we will discuss a little bit of analysis of this parallel algorithm, and also the speed up with Amdahl's law. And after that, the second part will be taken care of by Dr. Gokarna Sharma, who will mostly focus on possibly the hardware part. And in this way, we will wrap up after 5 days and 10 hours kind of. So, so what is a better computer? So when talking about the better computer, there can be many different types of definitions actually. So a better computer can do the same thing faster. For example, like Amdahl's law has defined, came up with this law which can tell me how much speed up we can get from a computer, from a processor, something like that. Also, the computer can solve a bigger problem. For example, let's say your laptop versus a data center server. Those are able to solve bigger problems. So, also, not only that, it is also possible a better computer can do the same thing more efficiently. For example, the hardware and everything is designed in such a way or so that it utilizes the less amount of resources. So these are all the different types of definition of better computer. Also, another definition can be like it is doing a better, doing the same things with better accuracy, or totally doing some kind of new things. So all these things comes under a better computer. Now, so the bottom line is, if you want to get more and more speed up, not only the software, hardware also needs to be better. Both software and hardware should work in collaboration to get the actual speed up. So basically, when we focus on the hardware, we talk about, like, most of the time, the hardware must be faster and it must be cost effective, because faster hardware is like, sometimes in the company we have seen something like, let's say, the hardware is very much faster, but the hardware is at the same time costly also. So at that time, if you try to utilize more and more hardware, your application will hit the organization's cost consumption wall. The budget will be exceeded. So faster and cost effective, these two are the bottom line for a faster or multi-core computation. Well, nowadays, actually, there is another direction where the hardware are being customized for the specific need, and FPGAs are also in the picture, but that is not the focus of this course. We will restrict ourselves in the faster computation and cost-effective computation with multi-core processors. So, so when it comes to faster computation, that is the faster computation can be achieved using many different ways. For example, let's say without changing the programming model, just by changing the technology or better circuitry design is enabling faster computation. That's one way of having a faster computation. Then there can be like concurrency, like how to manage, let's say there are a couple of different applications, and the way you are managing the resources and time slicing the resources to access it by different operations, that the cumulative time is significantly less time the application can be done. So that's kind of concurrency. Now there is actually a rule called Pollack's rule. Cost of going twice as fast is almost 4x. So whenever we are trying to achieve the faster computation by concurrency, then we have seen, it's kind of an observation, that cost of going twice as fast is incurring almost 4x amount of price. On the other hand, if we do kind of a parallelization type of parallelization type of speed up, then it may be possible, like cost of going twice as fast is only 2x, because you are just increasing most of the devices, and then you are just dividing the workload on those two things. Now, well, we will discuss about the concurrency versus parallelism in later phases in more detail, but these are just to set up the ambience that, well, there are two different way we can utilize the we can make our application faster by concurrency or by parallelization. So not only that, whenever it comes to the domain of concurrency, parallelization, these threading, hardware, acceleration, all these different things, the entire domain is guided by several laws actually. So the first one is, of course, Amdahl's law, and possibly you may all have heard about this law, that many problems have some sequential components which limits the speed. So Amdahl's law basically deals with the diminishing return of adding more parallel processing units. So it basically says that you can achieve as much parallelism as possible, but it will be limited by the part of the sequential part. Then mitigating Amdahl's law, there is another law which is known as Gustafson's law, which tells us that often the computational intensity of the part that can be done in parallel grows faster than sequential piece. So let's say there is a computational part that can be parallelized, but according to Gustafson's observation, those parts are heavily utilized by many different works. So that's Gustafson's law. Then there is another law which is known as Dennard's scaling, which says, like, if you shrink the transistor in all dimension with the same factor and reduce the voltage with the same factor, then the frequency actually increases by that factor, and density is also increases by its square, and the power density where it remains constant. So these are all the different types of guiding laws which tells us which is like ruling the total domain of like speed up, parallel efficiency, and all these things, and how much speed up is possible, all these things. Well, so talking about Dennard scaling, there is an end of Dennard scaling which we have already observed in the past years, with the advent of like quantum tunneling, which means the further scaling needs significant change in materials, like the chemical composition of the materials that are being used, or the structure of all these things. So which is not even possible anymore, because silicon, I mean, in that way you have to come up with another better isotope of silicon or something like that. So if that is not happening, then we cannot achieve more speed according to Dennard scaling. However, there is a scientist, Moore, who observed that, well, although we cannot change the material of the transistor or material of the equipment, but we can double the size of the equipment, or we can increase the number of those equipment to do more tasks at the same time, to get the parallel things done, to get the things done in parallel and achieve some kind of efficiency. So that is Moore's law. So these are all the different guiding laws: Amdahl's law, Gustafson's law, Dennard scaling, and Moore's law. These four things are possibly guiding this entire hardware multi-core domain, and possibly it will keep on guiding the entire domain for years. So so here is a small technology roadmap, like just to show you how we are evolving and where we are moving. So first it started with like single-threaded machines or single-threaded processors, where actually the focus was on chip designing. I mean, how can we improve the chip so that it can do faster computation. So that dominated the previous era for several years. But after few years, because of the Dennard scaling and the quantum tunneling process, the frequency of the transistors have saturated and it cannot improve anymore. And at that time, what happened, since higher frequency cannot be achieved, so everyone tried to add some more active transistor on the active transistor on the chip. So that way, basically, you can improve the performance, and that's possibly the introduction of the multi-core era, when faster material or fast processing is not possible using one single chip, then add some more transistor on that. So that's the introduction of multi-core. So now what happens, now it is a whatever era we are in now, it's the era of multi-core computing. But already in some scientific group, they have observed several limitations in multi-core computing, where they have seen the capability is saturating because of power limit and cost limit. So now the technology is actually evolving towards a hybrid type of computation, or they are proposing like special purpose ASIC based hardware or something like that, where actually the lower level AND gate and NOT gate, they can use kind of a network switch, and they can change the entire hardware infrastructure. Hardware logic, hardware can be configured. So those are the part of FPGA, which is started getting traction in the initial days, but we will focus on these multi-core domain in this course, which is possibly the most popular way of achieving the parallelism nowadays. So that is this is the motivation of this course. And multi-core is very much popular, and do not ever think that FPGA will come means the multi-core will go away. No, that's not going to happen. There are many, and by saying many, I am talking about millions of applications are there who are taking the advantage of multi-core, and they are being developed, and they are producing very, very good result and performance benefit in different industrial applications and different research facilities. So and also, compared to FPGA or the special purpose programming, multi-core programming is significantly easier in comparison. So that's so what I am saying, never think that since special purpose computation or FPGA is coming, that means multi-core will go away. So they will reside side by side. Millions of applications are being developed using multi-core facilities. They will take the advantage of multiple cores, whereas possibly there will be some new applications. They will all take the advantage of FPGA and special purpose computing. So possibly both the technologies will stay side by side from now, in future. So that's a brief technology roadmap. So basically there are three different ways to improve the computers. Number one is concurrency and parallelism, like several processors simultaneously execute multiple smaller calculations broken down from a larger problem, which is kind of a can be achieved using in the software side, like using fork and join libraries, which is one of the core part of software development, multi-core software development or multi-core computing. And that software part I will cover for the first 5 hours. And then the second way to improve the computer is technology and microarchitecture, the way a given instruction set architecture is implemented in a particular processor, for example the power 10 ISA and all these different things. So that hardware and microarchitecture and other different types of hardware related issues will be discussed by Dr. Gokarna Sharma, and possibly as an electronics student you may find that part more interesting than what I will deliver for the first 5 hours. So, and finally, there is the last way is specialization and configurable hardware, and which consists of like FPGA, that is field programmable gate array. Although this is not a focus of this course, but we wanted to have Dr. Peter Hofste, who is the pioneer, who is a distinguished research staff member in IBM Research Austin and pioneer in this domain. But I'm not very sure whether he can attend this course or not. We have planned like that, but we have heard that his father passed away, and so maybe I'm not sure whether he can make it or not. But anyway, so these are the 3 ways to improve the computer. So in this course we are going to give you the overview of all these 3 different ways to improve the computer. So any question before going to the next part, before I start my fork join parallel library? So how can I check the chat window? Stop sharing and then like that? Nope. Oh, okay. So any question?
Yeah,
all right.
Yeah, all good. Yeah, please go ahead.
Sure. So if there is no question, let me go ahead towards the next part of the presentation. So here it is. And all right. So let us discuss a little bit about the fork join parallelism in here. So here actually I am going to discuss about the sequential programming. First I will start of course with sequential programming, and then we will talk about parallel versus concurrent program, and then we will discuss about the shared memory with threads and shared memory implementation with Java. So all these things I am going to discuss in this section, and mostly we will focus on, in my part I will mostly focus on this type of parallel fork join type of parallelism, where you will get some experience and hands-on experience with Java fork join library, and that's it. So let us start with our fork join discussion. So what is a sequential program and what is parallel program? So first of all, may I ask all of you a simple question? So what is your, so how many of you are comfortable with Java program and like that? So you can write down yes in your chat window, or if you are comfortable with program, or if you say no if you do not have any idea with program. I got 1 yes. All right, what about others? I can see 66 participants over here. All right, 2 yes. Okay, so I started getting lots of yes. So great. So if you have, well, perfect. So if you have a good idea of programming, possibly you can easily follow these programming, follow these parallel programming and fork join and all these things. Well, I got 1 not so fluent in Java. Don't worry, we are not going too much onto the detail of Java, and rather if you need some guidance on Java, I will provide you the link to my online lectures, which is like very short course, and you can learn Java in very small amount of time. I will share all those things. So perfect. I got 1 no and 1 not so fluent. So I will try to give you the idea. I will try to keep everything very high level so that everyone can follow. All right. So now let's so here from slide. So here, so here it is the sequential versus parallel program. So you, whoever is familiar with coding, if you have done most of the time, whatever code you have done, those are possibly sequential in nature, if you did not do any type of advanced coding or utilizing the distributed computing or something like that. So the sequential coding is one thing happens at a time. If you notice the programming lines, they are all executed one after another. So there is program is just whenever you execute it, it's just one single process, and everything is working sequentially. There is no parallel part in the program. So everything is basically the part of one single sequence, step by step. Now, whenever we remove this assumption, it creates a lot of opportunities, of course several challenges, but there are lots of opportunities also. What are the opportunities? Of course, the opportunities is if you just divide the big work among many different threads, among many workers, of course you can get a lot of performance gain, right? The work that you are doing in 1 hour, if you can optimize properly, you can do that in 1 minute. Or maybe sometimes it happen in the machine learning that a training process is taking like 1 month for over 1 billion of data. Now, if you can employ the parallel processing, distributed processing properly, you can do that month's training. You can finish the month's training only in 1 hour or something like that. So those are the different types of assumption, the different types of speed up you can get. And but of course, I mean, this programming with these type of things are a little bit harder. Basically this, so what you have to do in case of programming, you have to divide the work among different threads, and also you have to coordinate among all these threads. That is, you have to synchronize their work. So that's a big challenge, and that's what you have to take care of. The next is, when it comes to algorithm, you have to take care of like, how can parallel activity provide speed up? Well, always remember, all the algorithms are not developed to take the advantage of parallelism. Okay, so you have to reconfigure the algorithm in such a way so that it can take the advantage of parallel processing and it can provide some kind of speed up. So it's just like the fact, let's say the way our, in the entire world, just a funny story, the entire world, the examination process in designed in such a way it cannot take the advantage of parallel process, you know. So let's say if you are working by yourself in the exam, then you are finishing the job in some point, let's say 3 hours of time. Let's say you did not prepare something very well, and you started you started asking during the exam time, like, what will be the answer, what will be that answer, what will be the other answer, something like that. So do you think that is going to help you finish the question in 3 hours? Well, of course not. Although you do always, and many people actually to do some cheating during the exam, but well, the inherent process is not designed to take the advantage of parallel processing. All right, so these are different types of things. So the basic fundamental idea is what I am trying to say, that all the algorithms are not designed to take the advantage of parallel processing. They are sequential algorithm also. Not only that, the other challenge is data structure. Well, just think of something. There is only one data element somewhere residing in the memory, and when all the threads or all the parallel workers are basically trying to access that part of the memory. So of course, I mean, you have to select the you have to organize the data in such a way so that it can it can accommodate all those parallel workers, all those concurrent or parallel access. So those things are pose a significant amount of challenge. Although there are lots of opportunities, you can have a big speed up, big performance gain, but these things you have to take care of. And in the next few next few hours, we are going to understand how we can take the advantage of all these things with a very simple example. And also I will provide the working code so that you can try it at your home and modify the code so that for better understanding. So anyway, so here is a very brief history of parallel programs. So writing the correct and efficient multi-threaded code is often much more difficult than single-threaded code, of course, as I have told, especially when it is written in the typical languages like Java and C++ or C, something like that. So what we have done, we typically stay sequential whenever possible. We just wanted to avoid the parallel processing, but from roughly like 1980 to 2005, desktop computers got exponentially faster at running the sequential programs. So, well, whenever it comes to the personal usage or something like that, we didn't even feel like writing parallel or concurrent code, something like that, because the cheap materials, I mean, using the Dennard scaling, they were getting faster and faster and faster because of the transistor and something, and you really do not need to go very much parallel. But as the Dennard scaling told, the end of Dennard scaling, if you can remember, that nobody knows how to continue this, increasing the clock rate. Lots of disadvantages are there. If you just keep on increasing the clock rate of the processor, it will generate too much of heat. Then the relative cost of the memory access will become higher and higher. So this way it cannot go. So we knew this was coming. So we looked at the idea for utilizing multiple computers at once. And if you look at the early days of distributed computing or this type of parallel computing, there were computer clusters like Buell's distributed computing, like SETI at home, and all the different things. Those are early days of distributed or parallel computing, or so like which used the advantage of multiple processors. But well, those are practical only for the big projects, but not very much practical for personal machines, not even for personal research or small research groups. But fortunately, we are still making the wires exponentially smaller, as Moore's law suggested, that we can increase the density of the transistor, and then we can add more and more transistor on the chip, and we can gain faster computation. So why? So this is when the the era for the multi-core actually came. So here is a brief idea of parallelism versus concurrency. As these, both terms are very much, these are not standard terminology, you can say, but heavily used in the community. So it is very important to understand their subtle difference. Well, parallelism is like using extra resources to solve a problem faster. All right, as you can see in this animated image, that there may be one vending machine and there may be two vending machine. So let's say there are two queues of customer you want to serve. So there can be you can, instead of having only one customer care center or only one vending machine, you are just adding another extra vending machine so that each queue is being served by a different machine. So you have just increased the amount of resources to do the work. All right. Now what happened? Concurrency is the other way. Concurrency means correctly and efficiently manage access to shared resources. As you can see in this picture, in the right hand side, here there is only one vending machine. So what is a better way to utilize that resource? So that's concurrency. And here, as you can see in this animation, that one customer at a time from one of the queue, from either queue, is coming and going. So this is kind of an efficient way to utilize one single vending machine. So concurrency, there is limited resource and you are making it efficient by time slicing it to many different work, whereas parallelism means you are increasing the number of resources, the amount of resources. Okay, so in both the cases you have to manage the threads, and in parallel computations most of the time you need to access the shared resources. Then concurrency, the concurrency needs to be managed. Okay, so this is the difference between parallelism versus concurrency. So before going to the coding example, let me see whether there is any question from the student or not. So any question so far? Did you understand the concept of parallelism and concurrency? All right, so if you do not understand, or if you have any question, well, I got one question. Ambika asked, like, which is better, parallelism or concurrency? Well, that's a very open-ended question. Okay, so there are lots of things that will decide whether parallelism or concurrency. Most of the time I will answer both. All right, because both of them are serving, both of them are basically, you can say, the other side of two coins. Both of them needs to work together. For example, concurrency will help you to be in budget. All right, because you have limited resource, so, and access it very carefully. So that's concurrency will give you better budget and all these things. Now parallel, well, you are in budget, you are doing good, but still you want to be better, then parallelism. So that's how parallelism, that's what parallelism and concurrency, they all have their own motivation. So both of them are needed. So how can we use both of them simultaneously? Well, that's a good idea. So I will give you the idea afterwards. All right, so hold your patience, Ambika. So well, so for now, just to remember that, well, both have their own purpose and both of them needs to be managed properly in a system. Okay, so, and that's it. Any other question from anyone? All right, so once again, if you have any question, do not stay silent. Please ask me whenever it is, whenever it comes to your mind, or either you can write or you can ask me the question by unmuting yourself. All right, so now let me go to the next slide. So here it is a parallelism example. So as I told, parallelism means it will use extra resources to solve a problem faster, like increasing the throughput via simultaneous executions. All right, and here pseudocode for any array sum, for any arrays sum. So let's say we want to do the calculate the sum. So this sum we will use to understand the concept of this parallel programming or concurrent programming in future. Well, so well, although just sum is not a great example, great real world example, but of course I can say that this is the best way to understand this one. And these slides I have mostly borrowed from Dr. Sharma, and I am just utilizing it, and I will just try to explain it. So anyway, so here is an example of parallelism code. You can say, or you can see in here, this is the sum function, as you can see here. And in this sum, actually we have used a construct called for all. Although for all is not a construct in Java, it is not available in Java, but let's say this for all construct is kind of an abstract which in the backend do everything in parallel. All right, and now the point is, what you need to know, that parallel computation, whenever it comes to parallel computation or concurrent computation, those things are significantly different. They can take different shape compared to the sequential calculation. Just compare these two codes over here. This is the motivation of this slide, to develop your parallel programming or multi-core computing thought process. All right, that's what you can get in here. So first one, let's start with the code in the bottom first. In the function called sum range, we have passed three different parameters, like an array, then low means, let's say it is 0, index low, and int high, which is giving me the highest index of the array, the maximum number of element in the array. Then I am just using a for loop going from the beginning to the end of the array, and then I'm adding all the results, and that's it. So that's the normal way of doing the sum, right? Now whenever it comes to parallel process, then what you have to do, you have to divide this entire array into different workers, right? So what you have to do, you have to take different parts of the array and give it to different threads or different parallel or concurrent worker. Make sense? And then each of these workers will do their part of the sum, give back the result, and then they will add it, and then you again add the two numbers. So we can do it using a very easy activity inside in here. So let me just go back to the chat window, and let me ask you the simple question. Yeah, so Gokarn, Dr. Sharma already mentioned it. Suppose you are running a parallel program in a cluster that access the same memory data, concurrency needs to be handled. Oh, okay, so this is possibly the answer for Ambika. So anyway, so here, let's say, so let me take like two students, okay? So here, let's say the first name that I am getting over here is Nitin Agarwal, and the second name I am getting Bhavusar Deep. Is your microphone working, both the students?
Yeah, yes, sir.
All right, and how about Nitin? Or you can write in the chat window also. All right, so let me show you something. Okay, so first, Bhava sir, since your microphone is working, let me give you 4 different numbers and you just add it. Okay, so let's say 1 plus 2 plus 3 plus 4. What should be the answer?
Ten.
It will be 10, right? And now if I just want to do it using parallel worker, so right now I am one of the process, and I am just giving it is everything is executing in the sequence. So I am one of the process. In the same sequence, I have just called Bhavasar, and Bhavasar just added it for me. Now I thought that, well, I really do not want to do like that. Let's do it in a different way. So what I need to do, let's say I am giving Bhavasar the number 1 plus 2, 1, 2, and 3. And then Nitin, is your microphone working? Well, anyway, so and let's say others so anyway, so if so let's say Bhavasar, I am giving you 3 different numbers, 1, 2, and 3. So what should be the result now?
6.
6, right? And now let's say Bhavasar is one sequence, and in another sequence I myself is working right on 4 and 5. All right, so I will take care of the second part of the addition. Bhavasar already took care of the first part of the addition, and then I have to again do the things like, let's say 4 plus 5 and the entire sum I will get. So this is how everything will be managed. So that's the parallel way of thinking. It's not so there you have to manage how much portion you will give it to each of the workers, and then how everything will be how every threads will return the result, how you will join everything. Lots of different things are there. All right, so those things you have to take care of. So let us go to the next slide. So these are all the different things like inside this for all. By writing this for all, we are simply abstracting away all our challenges. But well, don't worry, in the next few lectures, the next few slides, we are going to reveal what is happening in the back end of for all. But this is just to give you the idea of parallel processing, how parallel processing works. All right, so that is one of the example here. So the idea is simply sequential means the entire data set is being manipulated or being added in one thread. Parallel means you have to divide the data, you have to assign those data to the threads, get the result back again, and then again add them together to get the entire result. So all these things you need to take care of, and that makes the parallel programming or multi-core computing a little bit harder than the sequential thinking, sequential process. So that's it. And so here it is. And now the concurrency example. So concurrency is basically correctly and efficiently managing the access to shared resources from multiple, possibly for the simultaneous clients. Now, so here is a pseudocode for shared chaining hash table, where these hash table, basically if you want to do a concurrent access to the hash table, here actually it will prevent the bad interleavings, which is very much critical to ensure the correctness. So for example, let's say you have modified the hash table at some point of time, and you just read the hash table at some other point of time, and they are simply just overlapped, and you did not manage it properly, there will be a big problem. You can think of this interleaving problem is similar kind of, let's say, a bank transaction account. So let's say your bank account is kind of a data set, and where many different transactions are happening. You are withdrawing money from the ATM, you are credit card swiping, you are getting the salary deposited on the bank, and all the different things are happening. And if they do not if they are not done in a correct way, there will be a big problem. For example, let's say you have done the credit card swipe, and then you got some salary, and then you did the credit card swiping. Now your balance is zero, and at the same time you are, let's say, want to withdraw the money at the same time. So, and the bank gave you the cash. What will happen? So that's when the bank will go in loss, and there will be, everything will be messed up, right? Although you may be happy because you got some more money from the bank, but eventually there will be a big trouble because nothing is being managed properly. No, the interleavings are not correctly handled. Or so that's what is the meaning of interleavings. How all the resources will manage the resource. I mean, how all the threads or the workers will manage the same resource. That's interleaving. So anyway, so that's the so at the same time, well, in the sequential execution, you really do not need to take care of any of the interleaving because everything is sequential. One is going after the other. But whenever there are two different threads trying to access one resource, of course you have to make sure which one should go first. Should this thread go first, or should the other thread go first? If the other thread goes first, is there any chance of being messed up, doing the messing up the things? If yes, well, then manage the things properly. So all these things you have to manage. So that's what the concurrency related examples. So that's the parallelism type of thinking, and this is the concurrency type of thinking. In one place you have resources, so you have all the computational resources, so you have to take care of how you can divide a big computation to many different workers. And in the other place, it's all about the resources. You have limited amount of resources, so you have to take care of the interleaving. Which worker will take care of the things first, which worker will take care of the thing second, which will come next, which is coming next, like that way. All right, so that's what the thinking process should be: concurrency versus parallel programming. So any question on these thought process? So let me go to the chat window and let me see if there is any question. So did you all understand what should be the concurrency versus parallel processing thinking? All right, please write down yes if you have understood, or no if you did not, and feel free to ask the question also. All right, okay, so I got several yes, so that's it. So that's about the parallel and concurrent thinking process. So now let's go into a little bit more detail, but after that we will start our demo program and all these different things. So now let's the shared memory with the threads. All right, so here the model that we will assume for our programming experience in this course, we will assume the shared memory with the explicit threads. So the old story is, of course, if it is sequential program, there is only one program counter, one program call stack, and everything is like happening in only one thread. Objects in the heap is being created by the memory allocation using the new keyword in Java most of the time. So, and well, here actually one thing we would like to mention, that new is, here we are talking about the heap, but we are not talking about the heap data structure. Heap is basically a segment in the memory where we are storing all these things. So that's different heap. So anyway, so also there are static fields in the class, so which are shared among many different objects. And so this is how that's how the old story looked like when there was only one program counter, one call stack, and everything is happening in one thread. Now, The other part, if you want to gain performance, you cannot go like that. You have to employ multiple threads. So there are a set of threads, each with a program and call stack. So each thread has its own call stack and program counter. And but the thing is, they all have their own program counter and call stack, but they do not have any access to others local variables. So for example, let's say thread one, let's say there is a set of there is a program where you have written like int a. All right, now thread a is executing on int a. Let's say thread a has a local variable for int a, and then so well, I do not have any pencil, so what I'm missing anyway. So here there is no whiteboard. If it was there, then I could easily explain it. So what happens, let's say you have a function, let's say f1 is a function, and inside this f1 function you have a variable called, let's say, int i1. All right, so f1 function contains one variable int i1. Now let's say you give the responsibility of one thread t1 to execute the entire function f1. So t1 has its own instance of the variable i1. Then let's say there is a thread 2 called t2 that is also executing the same function f1, and it also has i1. But always remember, these two threads are totally different. This t1's i1 is totally different from t2's i1. If there is another thread, let's say t3, which is also executing the same function f1 with the same variable i1, but that instance is totally going to be different. All right, so the point is, since they have all their different variables and different instances, each of them do not have any access to others. So there is no overlap basically. So everything is executing pretty separately. That's what we are assuming. We will assume in this thread model. So shared memory with explicit threads. Now, communication among the threads occur via writing the values to the shared location, which can be achieved by using this static type of variable or many different, or the global variables, class level variables, something like that. So once again, thread may have local variables which are separate from each other, although they may execute the same function. But if there is a global variable, thread can also access those. The shared location can be accessible. We will show some example in Java code, like what are the shared variable and which are the local and all these things. So this is a simple picture that will say describe everything. So here there is only only one program counter and one call stack, and all the heap of objects are basically executed by this way. And so that is it. And here actually, as you can see, there are many threads, many these things, and many program counters, and each of the threads have actually its own program counter and call stack, and they are actually utilizing the shared memory space in here. So now that is not the only problem, or I mean only model for parallelism or concurrency. Let's say there is a message passing type of models is there, which is like, let's say each thread has its own collection of objects and communication is via explicitly sending and receiving message. Instead of, let's say, we can do it either using some kind of shared variable, something like that. But here there is no shared variable or no shared places at all. So, but here all the communication among the threads are happening through some message passing type of things. One way is like writing. So just kind of an example, let's say shared memory explicit threads means assume that you are in a classroom and you have a blackboard. and you are writing something in there. So everyone can see that. That's shared memory with explicit thread. You are sharing the blackboard, you are sharing the memory space, or you are sharing some variables, the global variables or static variables. But message passing means you are just writing on your notebook. No one can see this until you are sending it in an envelope to someone in the form of a message. That's message passing thread. Okay, those two are different models. So then there is a data flow model where programmers write programs in terms of directed acyclic graph. We will learn a little bit more about the directed acyclic graph later. And then here in data flow model, a node executes after all the predecessor in the graph actually. So that's the DAG. So an example of these, like a cook is waiting to handed result of all the previous steps. So every step basically depends on its predecessor. So it basically have some dependency on the previous step. So that's kind of a data flow type of model. And then there is a data parallelism model, which is nowadays very popular when it comes to especially the big data domain, where like let's say there have primitive of things like apply function to every element of an array in parallel. This is the simple philosophy. Let's say you want to increment each of the element in the array by 1. So what you can do, either you can go each element of the array 1 by 1 and then increment. Access the first element, increment it. Access the second element, increment it. Access third element, increment it. One way is going sequential, but you really do not need to do that. Incrementing does not have any dependency, so just increment at once in parallel. That also you can do, right? So that's called the data parallelism. And many of the big data analytics framework are based on this type of data parallelism philosophy. So anyway, so here now let us start a little bit of to write the shared memory parallel program. We need to know some new primitives from a programming library. So where there are several ways to create run multiple things at once. And so those are thread, what we have. I'm just trying to summarizing before going to Java. And then there are like ways for threads to share the memory. Often just have threads with references to some of the objects, and then ways for threads to coordinate, or for example like synchronization. So for now, a way for one thread to wait for another to finish. There are many ways for synchronization, but what we will see is like joining mechanism. What we will see, like one thread will wait until the another will finish. So that's kind of the thread needs to wait like that. So other parallelism are there. So anyway, so before starting these Java basic things, I have already asked this question, that if you have the good knowledge of Java or not. So anyway, I'm not assuming that you will have very good knowledge of Java, but if you are familiar with like this normal programming construct, like let's say these some like array, which you can get in C++ also, or Python also. Those programming concepts are good enough. And also a little bit of, if you know the concept of inheritance in Java, like inheriting something from a variable or something like that will be helpful. Although it's not we are not going to make use of inheritance or something too much, but knowing that it will be a little bit helpful when you want to do multi-core programming. And anyway, you can, if you do not have any idea of Java, I always recommend to go over this Java 101 and Java 202 course that you can find in Institute website. So just I will share this PowerPoint and you can see this. So let's see these things. So let me just copy paste this thing and share in the chat window if you want to go over there. So this is Java 101 and Java 202 you can find over here. So these two courses, so let me just go to one of these and you can easily check. So here it is, the Java 101 course. You just need to open an account over here. It's entirely free of cost. And after that, you just need to click this 6 hours, this play button, and it will start running your Java. I mean, you can see all the lectures and everything. And not only that, the best part is here actually there is a DIY, do it yourself button. What you can do, you can go to this Java IDE and you can start writing your Java code while at the same time watching the video. So for example, let's say this video has some code in it. So instead of just watching the video, you can just keep on typing the code by yourself. So that's possibly the best way to learn Java. So 101 will give you the Java 101 will give you the idea of the basic of the Java program, like all the different concepts like data structure, what is data types, the functions, and all the different things. And then 202 will expose you to all the concepts of object-oriented program in detail, like inheritance, polymorphism, encapsulation, all the different things. So so that is it. But since if you have the basic understanding of all these Java programming concept, you are good to go. You can easily write Java, I mean, multi-core program. And in the end of the this course, end of the lecture, I will share the code also with you, and you can start from there. You can start managing the code from, I mean, editing the code by yourself. So let's start from this slide. So here actually, so what do we need from the for the parallel programming in Java? The first thing we need a library, a special library for parallel program, and which is called the Java fork join library. That's what we are going to use, and this is this slide is showing you what is the overview of a parallel program that you need to do. Whenever we will do any type of things, I will just follow this type of format. This is the general overview of this multi-core computing. So here we will so here basically first you have to define a subclass of java.lang.thread class. So this is why I was saying that the concept of inheritance will be a little bit helpful. So whenever you are deriving some class as a subclass of java lang.thread, you will get lots of different parallel computing or abstract or APIs as it is automatically, and you can just start utilizing those. Then whenever you will define, whenever you will inherit this thread class, then in thread class basically there is a function called run, which is known as an abstract function, which you have to rewrite, or sometimes we call it override, or you can call it overwrite the function. So you have to come up with a run, with your own run method, and you have to write that. Then let's say creating an object of class C. After that, of course, whenever you want to work with an object-oriented program, you have to write the object, and finally you have to call the object's start method, and that's the format of our code. Everything will look like that. So that is it. So here, let's say here is our, so well, before going to the parallel example, some of the array, let me just show you a demo code or introductory code from for Java fork join library. What are the different functions and what are all these different things available? So here actually, as I have created one Java program to demonstrate the implementation of different fork join type of things. So here, let me show you the output first. So here, basically what I have done is number of available. I am just trying to get the number of available core in the processor, then number of active threads before invoking a thread, and number of active thread after invoking the computation actually. And also we will see the how many, what is the common pool size also. Okay, so here see the code basically. Here actually there is a code called the new task, which is basically executing as a recursive action. Recursive action is a predefined class in Java library, which helps you to write some type of recursive functions. We will know about it later, but well, just for now, remember that if you inherit means extends with recursion, then you have to re-implement or override the function compute. All right, because that's an abstract function over here. So anyway, so let's see what we are doing inside this new task function. So new task class. So here actually I have created a load which will define just how much load we are going to give in that work, in that task, which is basically, in for the simplicity, we are just doing it as a simple integer or long type variable. Then let's say there is a new task. This is called a constructor function in object oriented program. This constructor function is something like a function which has the same name as that of the class, and inside this constructor basically you can initialize the variables, initialize the class level variables. So that's one of the reason we use the constructor function in here. And then inside the compute class, what we have done is we have basically created several subtask array. You can just create a normal array, or in Java there is something called list, and then you can create a list of different types of new tasks. So that's what I have done, because Java provides lots of inbuilt facility. So if you just search over internet with list, you will come to know that what is happening. So basically what it is doing, it is basically creating an array or creating a list of subtasks of type this new task. All right, and then what it is doing, it is basically it is creating each of these subtasks. So calling the subtask method. So what it is doing, let's see what we are doing inside this subtask method. So in this subtask method, basically we are creating a new subtask over here, and here we are basically creating several new tasks. And let's say the first task is subtask 1, the second task is called subtask 2, the third task is called subtask 3, something like that. And then we are adding everything to the subtasks array, and we are returning that entire subtask. So let's say right now I have 3 different subtasks, and we are returning this entire thing. And these 3 different subtasks are basically added here in this example. All right, and then here what we are doing, we are basically creating so 3 for each of these subtasks. We are calling this fork function. Now this fork function basically creates a thread. All right, so what does this mean is this subtask, which is so this each of these subtasks here, they are basically being executed by a thread. So fork means subtask in subtask. So let's say this subtask can take the value of, like, the first subtask will go for, like, the subtask 1 will go for the thread 1, something like this is happening over here. Then subtask 2, let's say st2 will go for thread 2, something like that. And then finally this, let's say subtask 3 is going for thread 3. So this thing is happening over here just by calling this fork function in a for loop. So every time we are calling a fork function, it is creating a new task, I mean a new thread for that particular subtask. All right, so here as you can see, we have created like 3 different subtasks over here and over here, as you can see, and we are just creating different threads for all those subtasks. So now here basically this Java fork join intro I have called the main function, which is basically using several constructs to run this program in different threads. So here basically the first part is basically calculating the number of available processors in the machine. Then the second part will take, oops, so will this common pool functionality will take care of will create an how many threads and everything are available inside the fork join pool. That can be seen by using these fork join pool libraries, fork join pool object. And there is a function called get active thread count, which basically returns the number of threads that are currently working. So basically this line of codes, this line number 55 of this code, it is basically saying that, well, how many codes threads are there. But remember, still we did not started any of the task, we did not create anything. So this line is before the invoking any of these tasks or any of these thread. And then after here we have created the task with a sample load of 400, which will be distributed among different threads, different subtasks. And after that we have invoked all the threads, all the works and subtasks, everything. And then we are checking the number of thread count once again. And finally we are checking what is the pool size Java has initialized. So now if I just run this entire code over here like this, you can see everything in action basically. So so here it is an action. So here it is the numbers basically. So here number of available cores in my processor is 12. Then active threads before creating everything, before invoking the function, it is like 0. Of course, the function, the thread creation did not start. And then let's say for each of these new tasks, how many threads have been created totally, that is being returned over here after calling this invoke method. And then the common pool size, how many threads are available in that pool, that is written here. So as you can see, for this code, on almost 6 different six different threads are being invoked for this code. And so these are the different things. And let's see, so here are the different libraries. So get active thread count is going to give you the total number of threads. Get pool size is going to give you the total number of threads that are available for this computation. And available processors is a number which will give you the total number of multiple cores that are available in your machine. Okay, so that's are the basic code for to start working with the Java thread pool library. And you can just, I will share the code and you can just run it at your free time, and you can come up with the question in the later lecture. So next is basically, so here actually so now after you got the idea of this Java fork join library a little bit, now let us learn a little bit about the parallelism example, how we are doing the parallel computations actually. So let's say there are 4 threads simultaneously, some like 1/4 of the array. So here basically we are creating 4 different thread objects, each given a portion of the work. So let's say this is my entire array. So the first part will be added and then come up with answer 0, or let's call it 0th part or something like that. Then this part, 1th part, will come with answer 1, the next part will come with answer 2, and the next part will come with answer 3. And in the next phase, you all have to add this answer, all the answers together, to get the correct results. So that's what the parallel processing mindset that we have told, right? Now, when it comes to the actual Java code, it may look like this. The class SomeThread extends Java lang.thread library, and here actually, as we have done, like here there is a constructor function, as you can see. It has the same name as the class, and here I have just initialized these low, high, and array with some variable, and then just created the run machine. So I mean this run function, which is basically adding the number from low to high. But here, remember, our low and high is quite different because we are dividing the numbers. It's not just one threaded. For the first part, low is 0, high is maybe 4. Then second part, low is 5, high is maybe, let's say, 9. Third part, it starts from low is 10 to, let's say, 15. That's the third part, low and high. So like that way. So anyway, because so here actually we have to, since we are not returning anything, as you can see, this is a void method, we are not returning anything. So if we need to communicate, we will use some kind of global or like globally available fields or class level fields to communicate across different threads. So this is how our first set of code looks like. And so here actually we will ignore handling the case where length mod 4 is not equal 0. So we will always assume that the total number of elements that present in the array is divided by 4, like 100, 200, something like that. And then the responsibility is you have to create the threads. What you have to do, you have to write this function over here in this white area, as you can see. And this is the SomeThread function, is exactly same as I have discussed earlier slide. And here in this function, basically the sum of the thread. So here, if you see this TSI line here, we are actually creating the thread. So new SomeThread, and then in each of the thread, we are passing the value for this low and passing the value for this high and something like this. All right. So in this way we are doing, and finally in the answer phase, we are basically adding all the answers. So basically we are doing this part. So answer 0, answer 1, answer 2, answer 3. This is the first part of the array, second part, third part of the array, fourth part of the array, and then adding all the numbers. So that's what we are doing in here also. So there are 4 different parts of the array. We are giving the responsibility of adding each part in a separate thread, and then finally we are adding all those different things after getting the result from each of these threads. So now now the code is still incomplete. So what can be the reason why it is incomplete? Now we have created the thread. So what is the remaining part? Anyone in the class? Why it is incomplete code? So any idea? All right, so the main reason it is incomplete, it is because this code is incomplete because we did not start the thread. whenever you are assigning the things, whenever you give everything to the thread, the responsibility and everything is assigned over here, you wrote the structure of the code, but you did not start the thread till now. So you have to start it. So what you have done, we have just written the dot start method. So each of these threads, after assigning the portion of the data that it will compute or that it will add, we have just called this start function. Here, remember, it is a start function. It's different from the run function. All right. So, and also here we are just adding all these answers and everything using the same functions, TSI. And then what? It is still incomplete. Why? Because we started the threads and then we have assumed that it will finish right away, but it may happen because of the processor allocation, because of the memory allocation or the resource allocation, or for some other reason, one of the thread is taking more time than others. So what can we do? It is still incomplete code then. So let's say some code is basically finished and then give its result back, but the other part of code is not giving the result. So the entire sum, whatever you will get, that will be wrong, right? Because you did not get back the answer from many different places. So you need to wait for something. So here comes the join method, which basically tells the wait for thread, wait for some threads to complete. Why the name join? Because thread means it is forking. There is a main sequence, and from this main sequence, we have fork a thread. Now, join means this main thread will still wait until the other thread is joining the same path of the program. That's why the name of join. Actually, it means one thread is basically waiting for the end of the other threads. All right. So that's the join method. So the thread class. So the thread class basically defines the various methods that provide primitive operations. So join is one of them. And here join basically the color blocks until or unless the receiver is done executing what I have told. So you can get all the information inside this slide. So like that. So after knowing this join operation, now we are all set to write the complete code. So now the complete code looks something like this. Here, before adding all the answer, you have to wait until all the threads are finished and it gives back the result. So add another extra line before this answer, that tsi.join. So these join will wait for all the threads to complete, and after that it will get the result back. So now the code is correct, but what we have still do not have any control over, that the completion order is totally non-deterministic. It's not a concern, as our threads do the same amount of work, but we are not guaranteeing that all the threads will complete in the same time. So anyway, so that's the finished code. So, and I will share this finished code in with you also after the end of the class. So the finished code you can see in this demo.java function. So here basically, if you just check, let me just comment out all these different lines over here and over here. So let's say this is, so in here, so here is a complete version of the code basically. So here basically this code actually illustrates how the fork and join, all these things are happening. So this is a totally running version of code what I have explained. And if you just run it, so here you have to run it in here, and you can see the entire sum is being calculated properly. All right, so this is the thread. Here we are trying to add all the natural numbers starting from 1 to these numbers. All right. So, and in this code also you will find a sequential version of the code, which is basically doing the basically calculating everything in the same way. I mean, in the same in one thread, just by like the normal addition. So that part is inside this add function. So this is single threaded version, and the other part over here, this is basically multi-threaded. So that's what this code is basically doing, and the explanation I have just gave you. So oops. So now the question is, so after once we written the, once we are done with the complete code, here is the question. So where is the shared memory? So as we have told, like we will use different types of fields to access, to do the communication, to do the sharing part of the memory. So here there are fields you can see in the entire code, like there are fields like low, high, array. They are all different types of fields or different variables which are being shared across the different loads, I mean across different threads. So these are the shared memory related things. And when using shared memory, the challenge and absolute requirement is to avoid the rest condition, which is like, which means that you have to wait actual amount of time in order to get the correct result. Otherwise, your result will be totally different. All right. So you have to use the join function properly, so to avoid the race condition. So anyway, now the previous code. Now, well, so we have seen the first version of the multi-core coding, multi-core programming, but well, that's a very basic code, and that code is a little bit written in a poor format. This is just for your understanding. Now let's say the code should be reusable. So what are the chances of improvement? Where are all the chances of improvement? So first is the code should be reusable and efficient across the platforms. So for example, here if you see the entire code, we have used the total number of threads as 4, or total number of division is 4. So that's not a very good coding practice. It's all hard coded. That is how many total number of codes will be there. So well, I hard coded it because I first ran it on my MacBook, which has like 4 different processors, and I tried with 4 different numbers. But right now I am using an my other laptop which has 12 different cores. So I want to increase the number of processors, right? I increase the number of threads also. So I mean, of course you have to parameterize that part. That's one thing. The next is sorry. So of course that's one of the things. So of course you have to take care of how many different threads are there, parameterize the number of threads total. That's one improvement. Number 2, so that whenever you will parameterize, it will run in all the different laptops, all the different servers. So it will calculate the numbers, and I have already shown you how you can get the calculate, the total number of processors. So by tweaking those 2 codes, you can take it an homework exercise, self-evaluation homework exercise, like well, calculate the total number of cores in your processor, and then add those many numbers of threads in your code, utilize those many numbers of code. So you can easily do that if I share those 2 codes with you. And well, so that's one thing, parameterize the total number of threads. Well, now the other part is we may want to utilize the processors that are available at that instance. Now, well, I have 12 different processors in my machine, or 12 different cores in my machine, but they may not be free. they may be utilized by some other applications, so I cannot utilize them. And sometimes also it is like, let's say the caller program, that is utilizing the part of the thread. Let's say the caller program, right now we are assuming one thread, right? But let's say the caller program is also multi-threaded. What will happen? So it's like there is one Java program, it just created multiple threads, and each of these threads again spawned or again forked multiple different threads. What will happen at that time? So before assigning each of these threads, you have to take care of the fact of how many threads are available now. And possibly this the pool maximum thread, fork join pool, the demo I have shown, the last line of the first code, that can provide you the idea of how many threads are available and how many threads you can use, something like that. So, but well, it's not that easy to come up with the optimal number, but that will actually give you how many threads are there. So that's it. And after that, let's say, so here is let's say, so here the other part is, though unlikely for the sum, then sub problems may take significantly different amounts of time. So I mean, sum is very basic operations. Everything is just like a plus operation inside computer hardware, which is very basic operation. So there is not a big chance. But well, each of the sub problems may take different amounts of time if you do not give proper portion of the data. Or let's say based on the characteristics of the data, some threads may take a little bit more time than others. So so that's actually is sorry. So that part is basically called load balancing thingy, because it is your responsibility how you will balance the load across the threads. So that's one of the big problems. So for example, let's say if we create 4 different threads and all the slow data is processed by one of them, we may not get nearly 4x speed up because of the load imbalance. So if let's say one of the thread is handling 90% of the data and the rest of the three threads is handling only the rest of the 10% of the data, then the longest thread, I mean, which is handling the most amount of data, that will end after a long time. So you may not get that much benefit. So load balancing is very important to give fair share, proper share, equal number of shares across the threads. So those things are very important. So the better approach, one of the better approach is, although it is a little bit counterintuitive, better solution will be like spawn as many bigger number of threads, significantly bigger number of threads rather than the processor. For example, let's say if there are only 3 processors, you may fork like 100 different threads, where like the extra worst case extra time is less than 3% it will be. And if, I mean, of course it can be more, but for the current understanding of this fork and join type of program, we will discuss like, well, we are not considering all the memory issues or memory contention and everything. We are just focusing on the multi-core part and not the memory and all these things. So assuming all the memory issues are taken care of, or IO issues are taken care of properly, there will be at most 3% of worst case extra time. Then
yes, Professor, sorry to disturb you. So you may think of concluding in 5 minutes or so for the day.
okay.
Yeah.
Okay, sure. I mean, I'm okay. I was also not sure that when should I conclude. It is 9:30 or 9:45
Yeah.
because we started a little late, right?
Yes, yes, yes.
Okay, so thank you. So well, here, all right, so let's just take another couple of minutes to wrap up all these things. So what I am going to do is I will start from this better approach in the next lecture. So what I will do after in the better approach, you can see some of the improvement, like using this divide and conquer and all the different things. And also I will discuss in the next lecture, I will discuss about how to write realistic program, which is they are not theoretically very different, but programmatic difference when which you need to consider during multi-core program. So anyway, those things we will do in the next lecture, that is tomorrow. We'll start from here. But before concluding, any question for today? I think one question Ambika wrote, can't other threads output be collected till the first thread, which takes long time, completes its output, and when we have all the threads output, we can output the result? Yes, that's what we are saying. You can return back the result, but if I have understood what you are trying to say, still you have to wait for the final result to, I mean, the final thread to get the output, right? Yes, you can work over a different data set and a different part of the data, different program, or different, you can spawn different process. That's okay. But for that part of the code, you still have to, for that part of the result, you have to wait until the last thread is finished, which is the longest thread. Make sense?
Yes, I'll discuss it with her offline, and we'll
All right, sure.
give some
Okay,
more examples.
so,
Yeah, sure.
sure. So anyway, so thanks a lot for attending today's lecture, and see you all tomorrow.
Yeah, thank you, Professor. Sorry for inconvenience in the start. Tomorrow we will find out a better platform, and accordingly we move ahead.
Sure.
Yeah. So thank you all the students, and thanks Dr. Das as well as Dr. Salma, and wishing you a great day ahead. Thank you.
Thank you.
Thank you for the great session.
Yeah.
Bye.
Thank you.